Joachim Breitner as the speaker of our second keynote. Joachim did his PhD in Karlsruhe on GHC optimization and a postdoc in Philadelphia. And now he's with DFINITY, the company that started out as a Haskell company and now is a Rust company. Besides that, he's a member of the GHC steering committee, so he's still involved with the Haskell compiler. And today he's going to give a talk about the many phases of isOrderedTree.
Thank you. Thanks for inviting me. It's nice to be back at MuniHac. It's a great thing. DFINITY stopped using Haskell. We're still a fun company. If you want to apply, talk to me afterwards. I mean, they have the logo here, so I have to do some ads. But despite us being a Rust company, I'm still going to talk about Haskell. And I'm going to talk about trees. So let's talk about trees. And I'm going to talk about the question whether a tree is ordered. And with order, I don't mean what the people in the British Parliament keep shouting. So is this order? Order, right. Okay, let's talk about order. Quick show of hands, who thinks this tree is a well-ordered tree? Okay, a few hesitant hands. I guess the counter check. Who thinks it is not a well-ordered tree? Okay, some people are just getting a bit vague. That's fine. This seems to be a tree that's nicely in order. Everything to the left is less than everything to the right of a node. What about this one? Who thinks that is still a tree that's in order? No, so okay, we got more hands. That's good. Yeah, it's ordered. So we allow duplicates. That's fine. It doesn't really matter for the purpose of this talk. So we allow duplicates. What about this tree? This tree in order? Okay, some people are shaking their heads because there's a 6 on the left, but it's greater than the 5 on top. Okay, so this is the intuitive idea behind the problem that I want to talk about. Let's try to make this intuitive idea a bit more precise and say what we really mean when a tree is ordered. So for the purpose of this talk, a tree is ordered if for each node, the value is the value of the node is larger or equal to all values on the left and less or equal to all values on the right. That's a sensible specification. Why is it interesting? Doesn't really matter for this talk, but you can build nice data structures based on these kind of trees where you know when you want to find an element, you look at the node and then you go left or right depending on whether the thing you're looking for is bigger or less. And that's precisely the property you need for that. And given a tree, it's an interesting task to find out, well, is this tree actually, does it have this property? And there actually, interestingly, there are multiple ways of approaching this problem. And I think I can roughly characterize all sensible approaches, there might be more, in 3 ways. You can go top down. So as you go down the tree, you remember what are the bounds that I'm allowed to be inside. So what do all values have to be less than and what do all values have to be greater than? And you pass this down as you go through the tree and you check each node. Or you go up, in which case you look at a tree or a subtree like this one, and you return, is this tree ordered? Because obviously you want every subtree to be ordered, but also what is the range of values in this tree so that as you go up again on the tree, you can check everything's fine. And these are actually 2 different approaches, and many people think of one, and others think of another one. And then there's even a 3rd way of doing it, which is in a way left to right. You just traverse the tree all the way from the left to the right, according to the right in-order traversal, and you check that as you traverse the tree, every node is, every element is in the right order. So there are multiple ways of solving this problem. That is already kind of interesting, you know, like might be good to see that once you think of a solution, well, maybe you want to think of another solution and compare which one you want to do. But if I were just to present you these 3 ways of checking whether a tree is ordered, then we would be done in 10 minutes. That's kind of boring. So what I want to do is I want to show you that all these ways of doing this, solving this problem, are connected by small rewriting of the code. We can take one, and then we can do little program transformations, equational reasoning, some stuff that sounds more advanced like defunctionalization, to get from one to the other. And it's all connected. So that's basically the outline for the rest of the talk. I will be live coding all these things. This means that you're welcome to pay attention to all the mistakes I make and shout in if I do stupid things as I do it, so that it's more interactive. Also, in general, I like my talks to be interactive, so just raise your voice if you have anything to say that might be more interesting than what I'm doing, which is possible, likely, actually. Also, there are some things I don't have to do, so if we run out of time, I'll just skip some of the more less interesting things we can skip without derailing the whole talk, so don't worry about starting a discussion. That said, I do have actually quite a bit of stuff, so if we go over like 5 or 10 minutes before lunch, then I hope you will, I forgot the word, but I hope you will do it. All right, so let's start. We need a tree, so we need a data type. It's a tree. Of course, it's Haskell, so we make it polymorphic, arbitrary value type A. And a tree is either an empty tree, which is called a leaf, and I'm using single letters just to make the typing easier. Or it's a node, which has one subtree on the left, an element, or one subtree on the right. And we want to show these later. So the one great thing about Haskell is you can do type-driven development. So type-driven development is really great. You think about the problem, you think about the type signature, and okay, it's going to be taking a tree and it's going to return a bool. And then you stop thinking. So you say, okay, I need to look at the tree. What kind of trees do we have? We have leaves. Yes, leaves are sorted. That's easy. Or we have nodes. And then, okay, what do I do? Let's see. I need to look at the left. So let's see. Maybe the left is already a node, then I'm done. So if the left subtree is a leaf, sorry, then I'm done. Or it is another node. In which case, which is great, because then I have some value to look at. And I can check that, it's a different name. Check that the y on the left is less or equal than x. And I also, obviously, I want to check that the left tree is ordered. And I can do the same thing on the right. Only here, the value needs to be greater or equal. So this is type-driven development at its best. Oh, it's complaining that I need an odd instance. Okay, we can do that. Obviously, these things need to be comparable. Say again? Oh, yeah. Thanks. Great. Anything else? Are we happy with that? You should all be complaining because this is a horrible solution. Because it only looks, it wouldn't catch, sorry, where's my slide? It wouldn't catch this one. It would compare 2 is less or equal than 5, that's fine. 6 is greater or equal than 2, that's fine, we're all good. People actually write this code if they're too excited and too about type-driven development, or it's maybe a interview kind situation. Interestingly also, this happens more likely in languages like Java, where you're really used to, is this a null pointer or not? If it's not, then you have these things. So this is like tempting. So there's a little thing on the side. Type-driven development doesn't always cut it. You still need to think, despite using Haskell. Again? Better types are always good, yes, right. Okay, so this didn't work, so maybe let's try not thinking, but rather being very close to the specification. And remember, we had a specification. It said the stuff blah blah down there. So we can write this down. So we say a tree is ordered if for every node something is true. Okay, what's every node? Every node is a function that applies a predicate, like a function that returns bool, to each node. So it applies a predicate. If the tree is empty, then there's nothing to do. If the tree is a node, then we want to apply the predicate to the node, or rather the values in the node. So we just pass all the arguments of the node to this predicate, and then we traverse. A very generic function to check that something holds at all points in the tree. So we can use this, and now we can put a predicate here. It gets the left x and left subtree node and the right subtree, and now we can implement the check here, which says for each node, the value is larger or equal to all values on the left. So for all values on the left, this is the values are on the left as less or equal than x, and then the same thing on the right. Okay, and we can give it a type signature. Unsurprisingly, it's the same one as before. And it's complaining that we don't have elms. Oh yeah, we need to write elms, so we need to write a function that looks at a tree and returns all elements in there. And that's quickly, easily written. So there are no elements in the empty tree, and if there is a tree, then the elements are the elements of subtree plus the actual thing plus the thing. All right. Okay. Now I'm feeling more confident because I just wrote down the specification of the problem and using higher order functions and all the nice things we can do in Haskell to write high-level code. And this is my starting point. And from here, I want to go to all the various solutions that we hinted at the beginning. So let's try to start rewriting this. And let's little, warm up. I noticed that I'm actually using this every node function only with the same predicate all the time. So maybe I can combine them too. I can fuse them together. I can inline every node here. So let's give this a name. So I haven't really changed anything. Okay. And then I can look at actual cases of the tree. So either the tree is a leaf, then we pass every node on the leaf, but every node on the leaf is true, so we know that's true. And here now we have a node. And at this point we can do equational reasoning. So we have every node P is a node here, and that's precisely the thing that's there. So we can just blindly take this part and copy it here. And we'll be doing this a lot of times during this talk, because this is the beauty of working with Haskell. You can actually reason about your programs, taking all these equal signs as equalities. Then we have this every node P here. Remember that we started saying isOrderedTree is every node P. So now we can undo this and say, okay, this is actually just isOrderedTree. And suddenly, there's no more mention of every node. So we specialized the function every node to our predicate, and we can do a little bit of cleanup here, because the P is only being used in one place. So let's just put the body here. And that's our second solution. Not much different from the first one, but we're going somewhere. Doing more of these exercises, we notice that here we are traversing a tree to get a list of elements, and then we're checking some predicate. Surely we can combine that. We can just go through the tree and just check the predicate on elements. No need to return a list first. So what we want a function that's called all_elements. Takes a predicate and tree, and it does the same thing as all P on elements P. Okay, we can do that again. And we're following a similar pattern here. We take the definition, the thing we want it to do, and then we start pattern matching. Okay, elements of L is the empty list. All predicates on the empty list is true, so that's true. And then again, we have the node. And we can start copying the equation here. So elements on a node is precisely this stuff here. And now we can use some, so we know that a predicate holds for all elements in a list if the list is a concatenation of two lists, if it holds for all sublists. So we can just distribute this call to all over all elements of this, all components. Right, thank you. And then, okay, checking all of a singleton list, that's a bit boring, so let's like this. And now we have all P elements L, which is precisely the thing we wanted to replace with. So we can actually take this equation here, apply it from right to left, and we end up with something that doesn't call all or elements, because it calls the all elements function. And we just derived that from the specification in a pretty straightforward way. And we can use this in this code. And it didn't change much, but it goes in some. All right, right. I keep making this mistake. It happens to me every time when I do like programming and copying recursive functions. So let's make sure it doesn't happen again. We can do this by using a pattern that's very common in Haskell, which is a local worker function. So I define a local function Go in a where clause, and I use this in my function. The advantage is I don't have to rename it when I copy the whole function. it also means that it's clear that the go function is only internal to the function. I can't call it from the outside, which is great for encapsulation. You understand this code and you know that there's nothing you have to understand about this code that isn't actually relevant for anything else but here. All right, so we already have 4 different solutions. Now for something more interesting. So far, it's not a very efficient solution because at every node, we call all elements on the subtree, and then we again go through the subtree when we do the go. So that like every level, you start a new traversal, so it's like quadratic in cost, if not worse. So let's try to get rid of this. And again, we want to create a new function that takes a predicate and a tree, and it does both all elements and go together. Okay, so it could be something like all elements p t and go t. Okay, let's try to implement this. And for the leaves, okay, it's simple. Go of the leaf is true. We see that up there. All elements on the leaf is also true. We remember that. That's true. And then this is more interesting. So we do the case split on the tree, and now we can copy the definition for go, which is this thing, and we can copy the definition of all elements for a node, which is this thing. Okay, now we need to reorder a few things. So let's put these all in lines. And reorder them. So we want to check P, we want to, so we can reorder these, of course, because it's just AND. Okay. And now we have 2 calls to all elements with 2 different predicates, P and less or equal than X. But really checking whether some predicate holds for all elements and then checking some other predicate for all elements, we can just check the conjunction of the 2 predicates. And we can do this a bit more formally, but in the interest of time, I'll just do it like this. So we take a predicate that checks both P of X and that y, and that y is less or equal than X. And then here again, we check that P of R and y is greater or equal to X on the right. Here. Yeah, this looks better. Okay, what have we gained? P of, thank you. Okay, wait, where's it? Oh, I guess I need to rename them. So I get all my fancy IDE stuff. Okay, what have we gained? Well, we can apply the equation again. So if you look at this, we have all elements and go with the same tree. That's precisely the thing we thought about that go should do for us. So we can just call go here. And we can almost get rid of the old go, but it's still being called here. So what do? Well, we need to somehow get into a form that we can apply this equation again. So we have go t, that's fine. We also need to have some call of all elements p so that we can use go prime. And here we have to be a bit creative, but obviously if we just say const true, the predicate is always true, then I didn't actually change the program right now. Just added a new predicate that doesn't do much. But the goal is, of course, to get this into the shape that we can apply this equation, and then we can just replace it all by this go prime. And this can go. Oh yeah, sorry. Here. Okay, this was the first few steps were just really simple, you know, changing some functions. But here we did something fundamental. We changed the complexity of the program from quadratic to, well, there's still some problem with like the functions there, but at least the traversal is only one traversal. That's great. And we did this all in small steps that we can trust that we didn't change the program, which is the goal of the exercise. For the next step, in the interest of time, let me not type the next function. What I did here is basically I took all these predicates, all these functions a to bool, and just gave them names and put them here. So really, the const true became const true, and these lambdas you find here again, and just gave them names here and here. Because what I wanted to now is do something that's called defunctionalization. It's more like it's usually, like most of the things I'm doing here are actually compile optimization techniques, but we can also use them on the source language to rewrite our code. And the idea is that it's really nice to think about functions that you pass down and compose them, but it's maybe more efficient to actually pass down data, or it may give us more insight in what's actually happening. So what I want to do now is, instead of creating functions of type A to bool, I want to create a data type that describes all the possible functions that I can pass down, and then only when I actually use the function, which is only here, I want to interpret or evaluate this data type back to the meaning, like the function. So, and again, this is mostly mechanical. So we create a new data type. Let's call it pred for predicate. And I'm using GADT syntax here just because it makes the connection close more closely. Because I'll just take these. I mean, these are the only ways I can build these functions. These are the only ways that I do use to build these functions. So I create a constructor for each of these functions with a name, with a type as it's there, but with the A to bool, the function I want to get rid of, I want to defunctionalize, replaced by pred A. So it's very mechanical, and it's so I have a constructor const true, and it's pred of A. And then I have constructors and LE, which takes a pred A and an A and returns a pred A. And I hope you see the connection to the function type up there. I also need this for greater or equal. And because I'm using GADT syntax, I have to enable the language for that. I'm not using GADTs here. This is really a plain data type. You could just write it using the normal syntax. It just makes it a bit clearer what's happening here. And then I said I need a function that takes this data type and turns it back into the A to bool function. So I call it eval. And it takes a predicate and, as I said, turns it into one of these A to bool things. And we pattern matched on the constructors that we have. If it's const true, then we return const true. So really, we're using precisely the implementation from up there. We just put a data type in between, so to say. So this is a data type. It has a P and a X. And then we can take this definition. Couldn't match expected type B. Thank you. Right. And now we need the odd instance. Okay. Is this the wrong function? Right. Oh, yeah, I see. This should be this one. And then we have this, and now we can use it. And again, we can't invoke the predicate directly, so we have to use the eval function. Okay, now we can use this in the code here by saying we don't pass down functions, we pass down values. Const true, we don't need these anymore. And then here we use eval. Here we use the constructors. Okay, so that's nice. Now we're in a world where we're passing down plain values and no longer functions. And it's not a value of its own, really, because passing down function is fine. But it gives us better insight on what's happening. Because now we can actually look at this data type up there and see, oh, these are actually all the only ways I'm building these predicates. And this tells me something. It tells me something that the predicates are of a very particular shape. Because either it's they're all a set of values, basically an open interval, or I restrict the interval by changing the upper bound to something that's closer or a lower bound. So really, now that I look at this, I see what I'm doing here is I'm describing possibly open intervals. And with this insight, we can change the type again to something that is closer to what we actually observe. So it's a more precise type that matches the values that we actually see. So an interval, the tuple, it may have a lower bound, it may have upper bound. So we use maybe in a tuple. And now we can replace all the occurrences of these constructors with functions working on intervals. So we'll have a function called full It's just an interval a. And we have a function called and LE and BE. And it will have essentially this type, but on intervals. Okay, thank you. And now we need to write them. So full is has no bounds, and then we want to a function that takes an interval and updates the upper bound. So it takes an interval and a new upper bound. But of course, if the new upper bound is greater than the one that was already there, we don't want to change the interval. So first we have to check that maybe we don't have to do anything. So there's an old upper bound inside the interval, and we check that if the old upper bound is already less than x, then we just return I. And in the other cases, we have the old lower bound, and I'm mixing LB whether it's the maybe value or not. I hope that's not too confusing. In which case we just set x. And then we want the same for, write it out, for the other one. Okay, and we need odd instances. Yes, as always. There we go. And we can use now we can use this. You could say algebra, the set of functions, instead of the constructors that we just written. So we go to the 8th iteration of our code, and we pass down these intervals. And of course now I need a different function to interpret the interval, or basically to check whether an element is inside the interval. So I'll write this in interval takes an interval and returns a Boolean. And since these are maybes, we can use the maybe combinator. So basically the idea is if it's nothing, then we don't, everything's fine. If it's just a value, this value needs to be less or equal than x for the lower bound. And then the same thing for the upper bound. And we can use this. Yeah. All right. So now we've refactored the code to have a much more precise type we pass down. It's no longer this nested thing of predicates or of functions, but really it's just a simple tuple with two values. But it's still an abstraction layer, and there's actually a cost involved, as we will see now. So that as a next step, I want to take all this complicated or separate stuff up there and just inline it into our function. So just basically don't think about the interval as a separate type with like helper function, but rather just put all the code in here. And we'll see that this actually gains us a little bit. I think there's a bit of benefit to be gained. So let's do the 9th version. Okay, full, we just copy the definition. Then here we have an interval. So actually the predicate we know has a lower bound and an upper bound. And then we can use the equation for interval, which is this one, and put it in here. This. Okay. Now, what about this AND LE? There are two equations for AND LE. One where we don't update the interval, and one where we do. But note that we've already checked something here. So let's see. Oh, I should replace the P with lower bound, upper bound. Okay. So we already checked something. So let's see. AND LE is checking whether the upper bound may possibly be less than x. But if the upper bound exists, then we know that we did this check. So we know the upper bound in the interval we got is greater or equal than x. So it can't be less than x. So conveniently, the first equation up there can never happen. So we're doing a check that's completely pointless in the context of our program. And of course, as an abstraction for intervals, we need to do the check. But once we put it inside the function where we use it, and we specialize the function here, we can skip this check. So we know that we can always take the second equation up there, and now this code becomes much simpler, because we know and LE in the second equation just updates one of them. And this one, same argument, updates the lower bound. All right. So now we have a solution, and this is basically essentially what I would expect an experienced Haskell program to write if they initially think of I want to do the top-down solution, because they pass down intervals bounds in a tuple or as two arguments. They may be absent, or they use maybe, and they update them as they go, because they know in the context of their program intuitively that they can just update the upper bound with x, because the tree is ordered, at least if it's ordered. But that's what they're checking. But we found a way of deriving this from the specification with much more smaller steps that are all well justified. There's one more thing we can do here if we care about performance, and I'll just do it very briefly. Once both of these bounds are just values, so once we're in the inside of the tree, we're no longer on the outside edges, then they're always both just values, and even in the recursive case, we're always going to be replacing this just. So there's a lot of maybe voodoo around, when for the most part of the tree, we really always have two bounds. There's always be a big and a lower bound. So what we could do is we could, and I'm not going to code this out now, but I'll just show you what I could do if I really care about performance, and maybe I should measure it before, but anyway, I could specialize this go function into 4 different go functions, depending on whether it's nothing, 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 just nothing, or just. The point being that the final one, the go just, which is the one you use most of the time in a big tree, because in the inside, there's no more maybe around. You do these checks here directly on the parameters. Probably you don't want to do this necessarily by hand. It's good to know that you can do it. And it's even better to know that if you optimize your code with GHG, with -02, it will actually take this function and notice that there's a lot of calls with 2 just values in these things. And it will actually give you something more or less like this for free. So this is a side note. But really, I think this is the one that I would expect for the top-down approach. Okay, so we managed to derive one of the 3 variants. So let's go the other way. And I'll start again from somewhere up here. I'll start again from this one. Because now we want to go towards the bottom-up approach, where information flows. 11. Thank you. Oh, and yeah, okay. Let's really recursive functions, they're not local, are a bad idea. So let's do this. Okay, this is basically just isOrdered 2 with a go function. So we want to go up. And the thing to note here is that, again, we're doing 2 traversals. We're using go to find out if it's ordered, and we're using elements to get the set of elements. So can we combine these 2? And yes, the answer is yes, we can. And it's going to be a bit hairy, but we can go there and see what happens. So we want to have a new function here that combines both the effect of go, which is checking whether it's ordered, and the effect of the elements function. So we do this, and again we do the same kind of transformation. So for the leaf, this is true, and we on the empty list, that's easy. And for the node, we can start copying the code. So this is the code for go in the node case. This is the code for elements. Let me fetch that from up here. Okay, now we can go wild and refactor this code. So really, we don't want to call elements ll. We don't want to call it go l. We want to use go prime. So let's, and we know that we can get these things from go prime. So let's call go prime on left. and then just get out the, is the left sorted, what are the elements on left from here, and the same thing for right. And then we use them here and here, and also here. So again, we wrote the equation that we want. We inlined some code. We made sure that we call the same function recursively. Also, we have to do it here. So we want to call go prime on t, but we really only care about the first element here. Okay, so that's one way of that going this direction. Now we're passing up more information from the trees, and we're using this information. And let me give you the type signature of go prime just to verify what's happening here. This is takes an odd a, tree of a, and returns a bool and a list of a, and we don't need. All right. So what we're going to do next? So we're going to notice that really, once the bool turns false, you don't really care about the list anymore. Once this boolean is false, all of these things are going to be false because it's just and everywhere, and in the end we return only the first element of the bool. So really we're passing up too much, and the types are not precise. And what I really want to do here is have more precise types. So I want to say that instead of true XS, which is the one I'm interested in, I'm going to just be using just XS. And then if it's false, well, I'm going to be ignoring the list. There's no point in passing it out if it's already false. And using this as a guideline, this correspondence that I want to apply here, I can rewrite the code. So instead of returning true empty list, I return just empty list. Now this becomes, the type becomes maybe list of A. And now I can very conveniently use the maybe monad, which basically allows me to do lots of functions that return maybe, and just fail, return nothing if any one of them returns nothing. So this allows me to clean up this code a little bit, because I'll just use the do notation to call go on the left, and if it succeeds, then I get the elms list, and the same for the other direction. Then I want to somehow do these checks. There's a function called guard, which takes a boolean like this one, and if it's true, then everything's fine. If it's false, it returns nothing, so it aborts the whole computation again. And then I want to do the same thing direction. And we don't need to pass these OKL and OKR anymore because it's all handled by the maybe monad. And in the end, we return the, like if everything's fine, if everything's still sorted, we return the list. Now I need to import some functions here. Because also, in the end, we want to know, is this just? Like, did we not fail at any point in the process? Okay, now we're still passing up information, but we now have a more precise type. We use a maybe to encode whether it's sorted or not. And then the content is the list of all values. So let's do some local refactoring. We notice that it's really pointless to check, well, it's not really pointless, but we're checking whether all elements of a list are less or equal than some x. There's a better way of doing that. It's basically asking, is the maximum of x, maximum of the list, less or equal than x? The maximum is then all are. And here, of course, minimum of the right, greater or equal than x. So what's the problem with that code? Say again? Oh yeah, we need to, this completely crashes if we apply the empty list, and there will be empty list, so we need to check that first. Oh, thank you. So we want to check this only if the list is not empty. All right, that's nice. But there's an interesting observation we can make. Actually, we don't need comments. For these particular lists, I'm claiming that the maximum always happens to be the last one, and the minimum always happens to be the first one. And we can do some hand-wavy proof to check that. So empty list, okay, that's true. So here, the maximum, well, either this is a non-empty list, but then this maximum of this thing is greater than x, and x is greater than the maximum of this thing, so really the maximum is in this list, and it's the last one by the thing we're gonna prove. And if this is the empty list, then the rightmost thing of this list is x, but x is larger than everything on the left because of this thing. So really, no point in checking maximum minimum. You can just take last and first, or ahead, which is arguably a bit more efficient. And I was going a bit fast here. Like, you might want to, you can actually prove this more rigorously using pen and paper style equation proofs. But for now, it should be enough. Because really, what I want to get at, I'm only ever looking at the first and last element of the list. So what's the point in returning all the other elements? There isn't. So really, when we have a list like this, then it should be enough to return A and B. Well, unfortunately, we also have the empty list. So really, we need like another nothing, another maybe around it. So now we use this kind of abstraction or refinement of the types because that's all we need to know. And now I just have to update the code. So the empty list, I'm returning here. So nested maybes aren't really the greatest style, but for now, let's go with it. Okay, now we have to do a different check here. So we know that LMSL is a maybe of a tuple. So if it's empty, then everything's fine. If it's not empty, then we want to check that the last element, which is the second one, is less or equal than x. And then the same thing for the right, just going the other way here. And now we have to change this code. So we need some... thank you. Very cool. Cool people still paying attention. And now we need to do this differently. So instead of a singleton list, we return just the XX, which is a list that has x as the last and the first element. And then we need to have a different operator here that combines these kind of things. And it's pretty simple. If one of them is nothing, then nothing changes. I mean, nothing changes, doesn't really change. Nothing is immutable. And then in the other case, we have something like this. We have two just, and we're really only interested in the outermost value. All right. Now we have a bottom-up solution that has more precise types. Again, there's like one step further we can take, which is questionable. In this case, the questionable step is to notice that really this whole just nothing is only there because of the empty list, empty tree. Once we have a node, we know we will return a tuple like this. So maybe we can specialize Go to one variant that actually only works on non-empty lists and get rid of the maybe stuff. The code that we get from there is not pretty, but it might be like there's less maybe stuff around. It's more like an idea of something you could do. It's also partial, like Go n will just crash if you give it an empty list. But you don't need this strange operator that I defined up there. I haven't done any profiling yet. I would assume it's faster. This one's fast. Oh, sorry, top-down versus bottom-up. I would assume that the top-down is faster just because the types are simpler, in a way. But actually, it would be interesting to find out. I didn't do that yet. All right, that was the second of the 3 legs I want to go. So time for the last one. And actually, that's a pretty small step. And I'm starting with isOrderedTree. Remember, this is the one where we return a tuple with a Boolean and a list. I think we're at 17 by now. So again, I'm staring at this type here. We return a Boolean and a list. And I'm noticing, after some thinking about this code, that really this is redundant. Given this list, I can always find out what the Boolean is. Does anybody have an idea how? Precisely. I claim that this Boolean, whenever you have this kind of tuple, is always true if this is sorted and false if not. So let's go through it quickly and see if that makes sense. Empty list, yeah, that's sorted, that's great. And then here, if we take a sorted list, if any of these are non-sorted, then this is false and this is false, but then the whole list is non-sorted. If both of these list elements are sorted, but I combine two sorted lists with a value in between that's greater than everything on the left and less than everything on the right, then the whole list is sorted. And again, I'm a bit more hand-wavy than I might want to do. Like if this was more a course on formal verification, I would spend much more time on that. But it seems plausible, at least, that whenever we have a B and an XS, we know that B is, let's call it sorted list of X. So really, there's no point in returning the Boolean here, because it doesn't really contain more information. So we can just remove all that. Sorry. Yes, one moment. And then instead of first, of course, now we don't want to get the first element of tuple, we got to know sorted list. But we have to write that first. But that's actually simple. So we have a list. We want to know a Boolean. The empty list is sorted. A singleton list is sorted. And list with at least two elements is sorted if the first one are in order. And the rest list is sorted. Important, pass y colon z z here, otherwise you'll fail the interview. And as always, we need an OR instance. Okay, now this is a very neat solution. And somebody pointed out that now the Go prime is just elms. And it is. But instead of just replacing with elms, I want to do one thing. If this was real code, we really shouldn't be using the this append operator here, because it's slow and quadratic and stuff and bad. So we probably want to use something like difference lists here. The difference lists take the idea that you get the remaining list that you want to append, and then you append it. So this becomes function composition. This is just xcons. If you haven't seen difference lists before, this is not a full tutorial, but it's really simple. You can actually use it. You can use it in your code without pulling in a library. Like using a difference list in some code that you write is easy, and it gives you a big performance. There's one last code I wanted to use, because really, programmers should be lazy. So really what we should be writing here is to a list, and then, well, it says, oh, operations. It says to list not in scope. Okay, that's in data foldable. And I get this for free if I say deriving foldable. And I need a language extension for that. And really, this is the solution. That is. All right, so we have 19 different variants of solving this problem. Let's have a look at, testing it. And yes, great. Time is good. So I'll load the tree. I have a little test library. Thank you. And it defines an arbitrary instance for trees, so I can get random trees. So I can say quick check. Oh wait. I can say quick check, take a tree and say is ordered. Got one tree the same as is ordered. 2, 3. And it'll say 100 tests passed. Fine. Good. We tested it. Now we're feeling much better, right? Let's see if we have reasons to feel much better. We know that we wrote this one wrong instance before. Oh, it's passing. Still passing. That's bad. We remember the first one was wrong. So what is the problem? Nope, not the problem. Let's use the verbose check to see the kind of trees we're checking. It's polymorphic. The type variable is instantiated to unit. All trees that have unit as the leaves are sorted. So even our wrong code does the right thing. So let's invoke the Richard here and say we say like service. Oh, sorry. Okay, this is hard. How do I get this scroll up? I can't. Oh, maybe. Oh yeah, I could just say quick check. So I'm using an explicit type application to say I want to use isOrderedTree at type int. I mean, I could do it other ways with type annotations, but this is one way of doing it. And now it still passes sometimes, but not always. Because indeed, randomly picking a tree that violates this property in the way I showed you is surprisingly hard. So when people say, yeah, I did quick check, everything's fine, I'm trusting it, then it's like, okay, how well do you know is your random tree covering all this stuff? But we catch it at least sometimes. And okay, but we had 19 different implementations. So I created a little code that takes a list of functions, and I have all functions, and runs quick check 1,000 times for each pair, and then in the end we get a little table, and it says, okay, okay, 1 is actually a 0. Maybe I should have changed that. I added later, sorry. So it says that the wrong version is equivalent to itself, and then all the other ones are equivalent to all the other ones. That's yay. We managed to rewrite our code, preserving the semantics. So all of these 19 functions really implement the same code. These two are just occurrences where even in 1,000 tests I didn't catch the bug. So if I run it again, I get a slightly different shape. So does this mean that all these 19 functions are really equivalent? Are all my rewrites that I did sound? And I'm not talking about laziness. I'm not talking about termination. I'm not talking about performance. There's one thing we've been missing, and this is like the final twist of the story. And let's use this at a different type. Oh, I need to, sorry. There's probably a better way of doing this, but works. Okay, I'm running this, and I get a shape that's much different. Any idea what's happening here? Right. So this is the right answer. If you look at this, we got a broken odd instance. So this is the code I'm using here. We have a data type ABC. It has 3 values. And I define an odd instance, and well, every element is less or equal to another one if they're equal, and A is less or equal than B, and B is less or equal than C. Perfectly fine. ABC, I've ordered them. I'm using this, and it breaks. It means that some of my refactorings were wrong. And the reason is that while I was doing these refactorings, I'm implicitly assuming that all the values that I deal with here, all the type classes, are law-abiding, that an odd instance really is, and the crucial property here is transitive. So if A is less than or equal than B and B is less or equal than C, then I expect A to be less or equal than C. But this is not the case. But this is code somebody else could write. That's a good question. Thank you. He was asking whether this now means that the code is wrong, or like this code is wrong, or my code is wrong. And that's a good question. Was I clear in my thinking that I am relying on this assumption? Did I document them in my code saying only use this with a lawful instance? These laws are not checked. And if this is like some security critical thing, maybe it's a bit on me to at least be explicit in that I'm relying on this. So I agree that we should never write order instances like this. And maybe we shouldn't use doubles and stuff. But did any of you think about this while we're doing refactoring? And I think the 2 points I want to make here. The one is that, yes, type class laws are really useful because they allow us to do this kind of reasoning. And this is not just for odd, where they're pretty obvious, but also for monad and maybe and monoid and all these things. And sometimes you get tempted like, does it really matter if my monad doesn't quite satisfy the monad laws? Well, it might, because something like this might happen. So on the one hand, I want to stress the point that type classes are so great because they come with laws and they matter and they're very useful. But also remind you that it can be very tricky to remember where you're actually relying on them because it's so natural in many instances. All right, so that was the live coding part. Summary, I guess, is there's more than one way to do it, even in languages that are not called Perl. And sometimes it's nice to see that, you think of the top-down or the bottom-up solution first, but really there are other ways of solving the problem. And then noticing that you can actually take one solution that you have and carefully restructure it and go somewhere else without risking to change the meaning of the program if you're careful. You do equational reasoning and all these other tools. Obviously, I don't really expect people to write down the code the way I did and then just copy and paste and read it. Like some of these techniques that I just shown you, they work very well just in your head. Like you look at the code and you think, okay, really this type could be some other type. So I'll just update the code without doing the rewrite too mechanically. And then the last thing, of course, was type class laws matters and are useful, and be aware when you rely on them. Thank you. And other questions? I think we have a few more minutes, at least.
Yeah, very nice talk, thank you. Do you have an intuition, or maybe, like we have all these rewriting steps, but it's not entirely clear to me how that then relates then to go, if we, towards top-down versus bottom-up.
Right, so I guess in this case, I knew where I wanted to go, and I was retrofitting that onto this rewrite. So I had these 3 solutions in mind, and I was trying to find a way to go there. So it doesn't give you an immediate way, like you have to know the direction in a way. And some of them it's pretty straightforward, like you look at a type and you think, do I need all the values that are in this type? Can I maybe change the type to something more precise? And this might give you some more insight. But this whole top-down versus bottom-up, it doesn't like emerge automatically from this mechanism. Yeah, can you go over there?
I could just comment to that your choice of a tupling optimization versus an accumulating parameter does kind of correspond to the top-down versus bottom-up approach, because in one of them you tupled the two, you tupled some results, and in the other one you added something you were going to pass down. Right.
But I guess the point was I knew I wanted to go somewhere where I'm going bottom-up. So whether to go top-down or bottom-up, it doesn't really tell you.
That's definitely a choice.
Yeah. And actually, I've seen people solve this problem in a mixed way, where you pass down the first, like the lower bound as a top-down and the upper bound in a bottom-up. That was in a language that has only doesn't have multiple value returns. So different languages lead to different solutions, and it was very odd. But I actually feel like I could take the solution and transform it into one where you do the the traversal in a way that comes out of that, because there's some similarity there. But didn't explore that completely yet. Any more questions before we head out for lunch? Well, then I guess thank you.
Thank you again, Joachim. So in a few minutes, we're going to head upstairs for lunch. David is just checking whether everything is ready right now.